Again, welcome to NOAA Boulder's 8th grade Science Days. If you're not familiar, NOAA is the National Oceanic and Atmospheric Administration, a federal agency dedicated to understanding and predicting changes in weather, climate, oceans, and coasts. Today, we are introducing you to Christy Smith, who will be talking about collecting data in our NOAA observatories. But before we start, we would like to recognize that we are all coming to you from traditional lands of Native communities who have substantial traditional knowledge to share with us. We acknowledge that our speaker today is presenting from the lands of the Arapaho, Cheyenne, and Ute nations in Colorado. All right, I am going to turn you over to Christy now. Take it away.
Thanks, Carolyn. Good morning, everyone, and thank you for joining me today to talk about how the NOAA Global Monitoring Laboratory collects data from the poles to the tropics. As Carolyn said, my name is Christy Smith, and I am the Field Operations Manager at the Observatory Operations Division at the Global Monitoring Lab in Boulder. So let's jump right in. What is the NOAA Global Monitoring Laboratory? We are a lab of scientists, researchers, and administrators who study how the planet's atmosphere is changing over time. We're mostly located in Boulder, but we also have field personnel stationed in the Arctic, the Antarctic, and the tropics. And all told, we've got about 120 people in our observatory, or laboratory, not observatory. So our focus is monitoring changes in greenhouse gas concentrations in the atmosphere, the Antarctic ozone hole, ozone depleting gases, air quality, and then incoming and outgoing solar radiation. Next slide, please. So what are we measuring and why is it important? Starting with the largest portion of GML's mission, our laboratory closely monitors greenhouse gases in the atmosphere. I said how they're changing over the long term, how they're changing over time. We monitor carbon dioxide, methane, and many other important greenhouse gases in a lot of different ways. So it's just a quick reminder, greenhouse gases in the atmosphere absorb solar radiation and help trap heat at the Earth's surface. And without the greenhouse effect, we would lose too much heat back into space and it would be too cold on the planet to support our life. So human activities have added great amounts of carbon dioxide to the atmosphere and other greenhouse gases since the Industrial Revolution. And the graphic you see on your screen is actually a plot of carbon dioxide that NOAA has measured at the 4 atmospheric baseline observatories that I'm going to talk more about. And you can see that that is a steady increase over time with some fluctuations for the seasons as we go along. The more carbon dioxide strengthens the greenhouse effect, trapping more heat in the atmosphere and eventually changing our climate. Next slide, please. GML also studies and measures the stratospheric ozone hole and ozone depleting gases in the atmosphere. Ozone located in the stratosphere, which is about 10 to 20 kilometers above our heads, protects us from harmful UV radiation. In the 1980s, scientists discovered that during certain times of year annually, the ozone layer in the stratosphere above Antarctica was completely destroyed. And it kind of builds and destroys every single year based on different conditions that exist there. Protection from UV can eventually cause skin cancer, more sunburns, impact wildlife as well. So it was actually a really big deal, and it still is. Countries across the planet joined together and banned substances that were depleting the ozone layer. If you look on the images on the right-hand side, you can see in October, the ozone hole is its most prominent, and that you can see it over Antarctica. So it's an image of last year's ozone hole. And then on the bottom left, you can see a graphic of the amount of ozone depleting gases in the atmosphere and how they've changed since the 90s. So you can see in the late 80s, we discovered what was going on. The ozone depleting gases were still on the rise as we were creating them and using them. And then around 1990, 1995, they were banned, and you can see them start to decrease over time as well into the future. So this is a really great example of how international cooperation can change our atmosphere over time for the better. Next slide, please. GML also measures aerosols, which are tiny particles lofted into the air. They can be tiny salts from the ocean, blown dust, or other products of combustion like soot. And each aerosol either reflects or absorbs light based on its shape, its color, and other properties. So GML measures how aerosols in the atmosphere either reflect or absorb light and how much are in the atmosphere at our different sites at any given time. And we do this to learn how aerosols affect the Earth's energy balance and the climate. So for example, an aerosol that reflects light prevents energy from reaching the surface, so that would have a tiny little cooling effect. And aerosols can travel a long distance. The photo on the bottom right shows the plume from a wildfire, which is all aerosols basically. That's all that smoke is, crossing state borders. So GML often measures aerosols generated very far away from our sampling sites. And then tying this all together, the Global Radiation Division of GML measures the incoming and outgoing solar radiation in the form of light, heat, and infrared radiation that our eyes can't detect. And these measurements help validate the energy measurements made by satellites in space. Are they correct? How correct are they? And then these data feed into climate models run by scientists that predict the Earth's climate, how it changes, and the temperatures that are going to be in the future. Where does GML measure all of our information? GML collects data about the atmosphere all across the planet. We have sampling sites on every continent, including Antarctica, literally from the poles to the tropics. On the left-hand side, you can see our atmospheric baseline observatory network. On the top left, we've got Barrow, Alaska, actually located in the town of Utqiagvik. Going down, we've got the Mauna Loa Observatory, located on the Big Island of Hawaii, the American Samoa Observatory, located in the South Pacific, and then the South Pole Observatory, located in the Antarctic. And the image on the right, the map, shows one of GML's air sampling networks, where every single dot on the map is a location where GML collects air samples to learn about the atmosphere. And because we want to understand the whole atmosphere, well mixed, most of our sampling sites are located away from cities and local sources of pollution, so we can understand what the atmosphere is doing as a whole and the background. And our observatories are located in even more remote locations than the rest of the network to get as far away from human populations as possible and to measure the cleanest air possible so we can see what the atmosphere is doing without cars and people and factories, everything like that. Next slide, please. All right, so let's take a break for questions. Alex has a question: what are normal CO2 levels? Well, right now, I think Mauna Loa just hit 420 parts per million CO2. The atmosphere is always changing over time. So pre-industrial CO2, I would have to go back and look, but it was significantly lower. That's a great question. Why don't I get back to you on that, Alex? Because that's definitely a good one. But it does fluctuate over time, but what we've seen since the 1800s is a steady increase. Two more questions. Let me answer them real quick. You mentioned that ozone depleting gases were banned. Who backed that plan? Well, it's actually from the Montreal Protocol, which was an international treaty that started, I believe, in 1990 and has been amended over the years to include more and more ozone depleting gases. I don't know exactly which countries backed that plan, but if you look up the Montreal Protocol, named after Montreal in Canada, you'll be able to learn more about that. And then Logan asked, is there a correlation between skin cancer rates and the data? I'm assuming this means ozone hole data. That's a really good question, and that's something to look up. Not being a biologist, I don't have the answer to that one. But Logan, you're asking a lot of great questions. The Logan School. All right, let's move on. Next slide, please. Okay, so how do we actually make these measurements? Now that you know what you studied, let's look at the different ways and platforms we have to collect all the data that NOAA does at our observatories and in the field. So the first way to measure gases or radiation coming in from space is in situ or in place. At observatories, we have sampling air lines that suck air in from outside the buildings, mostly from towers or other locations, and we send that air directly into the measurements, into the instruments to make measurements. And that's where the in place or the in situ comes in. The picture on the bottom left shows some in situ instruments. Those ones are actually measuring aerosols and ozone at the South Pole. And with these type of instruments, we record data locally. We're usually getting a gas concentration or an aerosol particle count. We record that data as a file, a computer file, and then we send it back to Boulder for analysis. Another way we take measurements is to actually take physical samples. And we fill several different kinds of glass or stainless steel flasks in our vast networks. We pressurize these flasks, which are basically bottles, and then send them back to Boulder for analysis on very sensitive instruments at our laboratory in Boulder and also the University of Colorado. Our techs use portable sampling units, and as you can see, that is the picture on the top left. The portable sampling unit is basically a suitcase with a pump inside it that we use to bring air into the flasks and then pressurize them. And once those flasks are filled, we carefully package them up and ship them back to Boulder for analysis. In the top right picture are the flasks that were filled in the field getting analyzed in Boulder. And we can pull, I think we pull, man, at least 20 or 30 different types of gases out of these flasks. So a great deal of information comes out of the physical measurements as well. So that's about the two different ways we can measure data at the surface, but our measurements also go vertical. So GML uses tall TV and radio towers in the United States to fill bottles of air at different altitudes from the surface as well. So they can get an idea of what's going on at the different levels as we start to leave the surface. The tall towers we measure from can be about 1,000 feet tall. So the picture on the bottom right shows a tower that GML used to use in Colorado that was 984 feet tall. And just for reference, the Eiffel Tower is just a little bit taller in France. So like we can go pretty high off the ground using just the tall towers. Next slide, please. And then if you want to go even further vertical, we can go higher by filling flasks with aircraft. So small planes have special air inlets that are installed to bring clean air into the aircraft as they fly. So they fly over a certain location and they fill bottles of air at different altitudes on that location as well. And then all those bottles of air get sent back to Boulder for analysis. Want to go even higher? Well, planes usually fly around 30 to 40,000 feet, but our balloons can actually go up to 100,000 feet. So we can send up different packages, different instrument packages attached to the bottom to measure ozone, water vapor, or other gases all the way up into the atmosphere with these balloons. The pictures on the bottom show ozone sondes being launched from the South Pole, and those are small little instruments. They're basically just sucking in air and measuring the ozone that it's sucking in. So those ones go up on a weekly basis unless the ozone hole is forming, which is around September, October, where we kind of ramp up our frequency of launches at the South Pole. So we're launching every other day to capture that ozone hole, and then we ramp it back down once the ozone hole starts to dissipate. All right, next slide, please. So a lot goes into making each and every measurement we do. First of all, we need a human on site to actually take the measurement. And we have technicians staffing our 4 observatories that I talked about full-time. And in a lot of our other sampling networks at GML, we rely on volunteers to fill those bottles of air at other sites. We also need supplies. The Flask Lab in Boulder processes about 20,000 samples each year, but then we only have about 5,000 or 6,000 flasks to begin with. So we have a full-time job of getting the flasks in, processing them, shipping them out, and shipping them to sites around the world. In order to make sure all of our instruments are reading correctly, we also have to do regular maintenance and perform calibrations on the instruments on a regular basis. And the technicians do this to ensure that we have extremely accurate data and measurements, so we know exactly what the atmosphere is doing. And then lastly, as I said before, we're really interested in clean air, measuring the cleanest air possible. So at observatories, our technicians closely monitor the wind speed and the wind direction. We have a clean air sector at each site where we know there is no population, no sources of pollution upwind, sources of combustion or contamination. So when the wind deviates from this clean air sector, we either don't fill those bottles of air and don't sample it, or for those in situ systems that are constantly measuring what's going on in the atmosphere, we can flag the data in our quality control process as being potentially not clean and probably not being included in the analyses we do with the data later. And you can see I've got a couple of pictures down here of our technicians working in the fields. The one at the bottom's on a tall tower. Well, not a tall tower, one of the towers, actually a pretty short one. The one in the middle is someone measuring ozone around. One on the right is we had to dig a hole in Antarctica to replant some of our solar instruments. And then the top right shows our clean air sector at the South Pole and the fact that about 90% of the time our air is coming from that clean air sector. Next slide, please. So it's a good time to take some questions. I'm also going to talk about environmental conditions now. So I'm going to take the time to put on the jacket that we wear at the South Pole that's issued to every single person who goes to Antarctica. It's very warm, very big, and it will keep you toasty down even if it's minus 100 degrees Fahrenheit, which it does get to be. I wintered there for a year, so I can tell you that this will keep you very warm. And I'm really not sure how long I'm gonna be able to wear this, but let's see what we can do here. All right, so I've got a question from Alex. How do you exclude the exhaust from the plane from the collection bottle? Oh, that is a great question. So I believe the inlets are positioned upstream of any exhaust from the plane engines. And that's kind of our concept of what we do at all of our observatories. You obviously need to have people, vehicles, power generated. So we want to make sure that our air inlets, no matter what we're doing and where we're sampling, is upwind of sources of combustion and sources of pollution. So those air inlets are upwind of any engine or exhaust. That's a great question. A question from the Boulder Science class. What is your favorite part about being at the South Pole? It's pretty remote. That's a great question. I think what I liked the most about it was being on a pretty small crew, which I'll talk about in a little bit, and being part of it that was working hard against the elements to get something done. It is very remote, it's very harsh. Another thing I really enjoyed was the Southern Lights, a lot like the Northern Lights, but in the Southern Hemisphere, because they put up just beautiful aurora shows every single night we were there, and day in the winter months. But I'll talk about that in a little bit. Great question. The Logan School has a question about how the deterioration of the ozone let me read this again. How does the deterioration of ozone affect health around the world? Oh man, that's a big one. So I'll talk a little bit about it and then we'll need to move on. It's got a little more to go. So the ozone hole over Antarctica basically destroys that protective layer in the stratosphere over the entire continent. Not a big deal because there's not a lot of people there, but there are some animals and some, not really plants, but some animals as well. And then when the ozone hole dissipates, it basically dilutes the ozone layer around the southern hemisphere, so you get less protection from UV radiation. So you could get sunburns easier, which could lead to skin cancer. And I know that someone was asking about that earlier. I think it was Logan School. Sounds like you guys need to do a little bit of biology research to follow up. So you've got a lot of really great questions about the ozone hole. So I definitely suggest you follow up after this talk and look a little more into that. Great questions. All right, I'm going to move on because I only have a couple minutes left. So since we measure air from the poles to the tropics, GML deals with every type of environmental challenge you can imagine. In the tropics, to start off with, it is very hot. So our people there have to be very mindful of taking care of themselves in the sun and the heat. We also have unique problems like instruments getting full of spider webs or mosquitoes or geckos that block our air inlets or get in the way of our solar measurements. So we definitely pay close attention to what is going on with our instruments on a daily basis to make sure they're clean and unobstructed. The sun is also, of course, very strong in the tropics. So there's a lot of UV radiation that makes our cables and hoses brittle, just like it would anywhere else, but it's very intense there. And in American Samoa in particular, which these three top photos are from, it's also a very tropical location, being located just on the ocean, and it's very salty. So in those tropical conditions, everything rusts very quickly. So we're constantly dealing with rusty instruments, rusty connectors, and we have to spend a lot of time just dealing with repairs related to moist conditions. At the South Pole and in Barrow in Alaska, it's the complete opposite. Our staff have to deal with protecting themselves from the cold. They have to wear special cold weather gear, bundle up, take breaks when they're working outside to go and warm up, make sure they're not getting frostbite. And in addition to UV radiation, which we do get at the poles, making things brittle as well, the extreme cold will make tubing and cables and lines stiff and brittle too. So we're always really careful working with instruments outside in the cold because it's really easy to snap a cable or snap a line, and then you have to do a whole repair to get your instrument up and running again. I just want to highlight the picture at the bottom was my coldest day during my winter, where we hit minus 103.4 degrees Fahrenheit. So it was a very chilly day. Next slide, please. So there's other challenges working in remote places. Shipping isn't fast. And remember that we need a steady supply of those air flasks to fill, to take measurements and send them back to Boulder. We also need things like compressed gases to help the instruments run or to do calibrations against. And then just regular supplies that you need to run an office or any other location. We need to order things well in advance of needing them. There's often few or no stores around, so you really need to think about what you're going to need if something breaks, or every scenario that could potentially happen, so you can have replacement parts or spares on hand in order to fix things. There's also very limited communications at some of our sites as well. South Pole has all the communications via satellite, and those satellites orbit the pole, so they're not available or visible all the time. So we get about 12 hours of communication via satellite with South Pole during the day, and otherwise they're basically in the dark without phones or internet easily. We also work in places that have very limited flights. So getting to an observatory can take days or weeks. Getting to Antarctica, for example, the weather's very harsh, so the planes will only fly there when it is absolutely perfect conditions and there's no mechanical issues as well. Yeah, but we get the privilege of working and living in amazing places. So I'll tell you a little bit about South Pole and our observatory there, since I lived there for a year. It can take about a week to get down to the South Pole with flights. It's about 24 hours of flight time. First, you start in the States and take a commercial flight to New Zealand, and then you take these planes that you can see in this image down to the pole on skis, and they actually land on the snow. Next slide, please. The South Pole is about 9,000 feet above sea level, so it sits on the Antarctic ice sheet. And your view is flat and white as far as the eye can see. And it really is a beautiful and harsh location to work. In the summer months, your average temperature is probably around -20 degrees Fahrenheit. And in the winter months, it can get down to -100, but it kind of fluctuates between -40 degrees and -80 as like your normal average range. The Amundsen Scott South Pole Station is run by the National Science Foundation. You can see that in those top pictures. And the main station holds about 150 people in the summer months. And then in the winter months, when the station closes, it drops down to 50 people. The NOAA Atmospheric Research Observatory building, or ARROW, is the building in the bottom pictures. And it's located about a 1/4 mile up the station. So someone was asking before about how we make sure we're not getting any pollution from combustion. We stay upwind, and you can see we've got a good distance down there. So, and anything upwind of the observatory, there's literally nothing there but snow for about 800 miles. And that area is protected out about, I think we've got about 100 miles protected upwind of us where no one can even walk or drive or fly. So we have very, very pristine air that we sample. At South Pole, the year's kind of broken up into 2 seasons. The summer season is when all the shipping and logistics happens, and that runs from November to February. And during this time, that's all of our food, our supplies, our fuels delivered for the next year. And most of that's coming in by aircraft, or there's a couple traverses where big tractors hauling a lot of equipment come in. And then in February, it gets too cold for the planes to fly as we're approaching the winter months in the Southern Hemisphere. So the station closes for the winter. And remember, because we're at the South Pole, there's only 1 sunrise and 1 sunset per year. So there's 6 months of light and 6 months of darkness. And in mid-March, after the sun sets for the winter, we don't see the sun again until mid-September. So everything kind of slows down, goes into winter mode. All the work continues for NOAA and the scientists and the support crew. We just do it on a very smaller scale and in the dark and in the cold, but that really is the fun part of it. And then about a month after sunset and a month before sunrise, you really get the bright, beautiful auroras. And you can see that in the bottom right-hand photo. It's hard to take a picture without an aurora in it sometimes. So yeah, we continue our science for the winter, and then the sun comes again in mid-September, and we start getting ready for the busy season again. And yeah, that concludes my main presentation. Next slide, please. I want to thank you guys for learning about how we operate at the Global Monitoring Laboratory and the different observatories. I've got time for 1 or 2 questions before I need to jet, and I actually am getting on a plane to go to the Mauna Loa Observatory today. So I'm gonna get rid of this jacket because it's gonna be much warmer there. But let me look in the chat here and see what we've got. Alex wanted to know how I wound up working at the South Pole. Well, about 10 years ago, I was a NOAA Corps officer, which is a uniformed service member who supports NOAA's mission of driving the ships and aircraft that NOAA operates. And one of the opportunities we had was to go to the South Pole. So I asked for that job and interviewed and was granted it within NOAA. And I got to go down and be a technician with the Global Monitoring Laboratory for a year. And I ran all of NOAA's instruments, did all the calibrations, and made sure all the data was flowing. And it was a lot of fun. It was a really great job. So I'd say if you're interested in science and field work, a great thing to do would be to look up NOAA Commissioned Corps. You've got an officer corps of about 300 officers who do exclusively field work and working in laboratories like this one. The Boulder Science class asked how old I was when I realized I wanted to do something in environmental science. That's a great question. I was not interested too much in science until high school. I really wanted to be an artist. And then I had some really great experiences with lab classes I took in high school. I found them very interesting and was very curious about the world in general. And I wound up studying meteorology as a great way to interact with the outdoors and a lot of physics and a lot of math. I've been interested in it ever since. So the Logan School is asking what brings me the greatest fulfillment in this job. And I have to say, working for NOAA, it's just really great knowing that what you're doing impacts the global community, especially at GML, where we're studying everything that impacts the climate. And when you start looking at what the weather's doing outside and seeing natural disasters and learning more about how the climate is shifting, it's really fulfilling to know that you're providing the data that's letting the scientists do the research to figure out what's going on and what our climate's going to do in the future. So I want to say again, thank you so much, and thank you, Carolyn, for organizing. And I've got a bunch of pictures after these slides, so I hope you get to look some more at our different observatories. Oh, I think you're on mute, Carolyn.
I was on mute. Thank you so much. Yes, Christy needs to run off to the airport. So thank you for joining us. I have some more to show you, as Christy said. So bye, thank you. So you can stay on and I will show you some more photos, and we'll see what's happening right now in our observatory with some webcams. All right, so as Christy said, there are 4 observatories, as you see here, and they are, they were chosen because these are places that, the U.S. could build observatories, right? Part of the United States, American Samoa is U.S. territory, South Pole is an international space. They're all away from a lot of humans and factories and traffic and all of that. They're a very similar longitude around the Earth, but very different latitudes. And so these are places that are really good to compare information that we get. All right, so these are pictures that Christy wanted to share about each observatory. The Mauna Loa Observatory, you would think would be more tropical. It is in Hawaii. It's on the Big Island. But once you get there, it does not have a tropical feel. It is at the top of one of the 2 big volcanoes on the Big Island. And it can snow. That is an actual snowman that they made and surrounded by snow in that bottom picture. So it does snow in Hawaii when you get to the tops of these very tall volcanoes on the main island. And so it actually can get pretty cold. But you just drive down the road and you're in what you would think of as normal Hawaii tropics. Here's the Barrow Observatory. Lots of snow, so you can see the snow removal that they're doing there. This is the far north of Alaska. They just got a new building, as you see here. So they're excited about that. It is part of a community. So there's a town there. It's not that big. You can look up how big this town is. But there is a community. They're on the Arctic Ocean, basically. So it's the very farthest part north of Alaska. American Samoa, this is the tropical location that Christy was talking about, where it's easy for instruments to rust and you have the heat to deal with. So it is not at a high elevation. They're on a bit of a hill, but they're not that far up. So it does get very hot, very humid, very salty, all of those things. But also, again, this location is a bit more of somewhat in a town and community on the island they're at there. So the folks that work in this station will live on the island, live in the community for many years, a lot of them. But also there are NOAA Corps officers who will go for a year or so at a time and work there. Excuse me, and then the South Pole Observatory. The South Pole is a very interesting spot. I have not gotten to go to the South Pole, so not speaking from personal experience, but as Christy was saying, about 150 people are there in the summer. And so some people will go for a few weeks. Christy's actually headed there, she said, in about a month to stay for a few weeks. Some people will stay for the summer, maybe 4 months. And some people, about 50, will stay for a whole year. And so for about 7 months of that time, there are no flights in or out. And so they do a lot of health screenings to make sure you will hopefully not have a health emergency while you are down there, because it's very difficult to get people out from the South Pole in the wintertime. Christy mentioned there's only one sunrise and one sunset. So on the first day of spring, which is September in the South Pole, that's when the sun comes up, so peaks over the horizon. So there's a bit of time when, it's getting a bit brighter. They're not quite seeing the sun, but it is getting brighter. And then they see the first sliver of sun on that first day of spring. And so then the sun slowly gets higher and higher in the sky, but it is always above the horizon. And that's what the Antarctic Circle and the Arctic Circle is all about. So once you get further north of the Arctic Circle or further south of the Antarctic Circle, that's where the sun is always either above the horizon or below the horizon in the summer or winter. So then the first day of fall in the South Pole, which would be in March, the sun goes below the horizon and they don't see it again for until spring, so for a whole 6 months. Patrick works for NOAA as well. He monitors ozone, and so he's in charge of sending up our balloons with ozone sondes. It's an instrument that is in this like styrofoam package that is attached to weather balloons. And they send those up from the Boulder area, from our observatories, from about a half a dozen spots around the world, about every week. And so that includes in the South Pole. And he's spent quite a bit of time in the South Pole. So he's also a great photographer. And so that's why his signature is on this one. All right. And so here's some instruments she wanted to share. I think we've seen some of these before. Some might be new. And weather balloons, so the ozone sonde. If you've heard of a radio sonde, that I think there's actually a radio sonde in this package as well. But all right, so if you see on the photo with the big weather balloon and that orange thing below it, that is a parachute. And so the balloon will go up to about 100,000 feet, and then it pops and comes down with the parachute, so it doesn't crash land, it more slowly comes down. And that ozone sonde then is measuring ozone all the way down. It has a radio sonde as well, and that is measuring air pressure, humidity, air temperature, and what am I missing? Air pressure, oh, and wind, wind speed and direction. All right, so you need a lot of stuff. This is some of the gear to get to the South Pole. That's that South Pole station. And getting all their things in that they need. Can you imagine seeing the Southern Lights or the Northern Lights about every night? Must be remarkable. So some nights would be brighter than others. If you're able to tune into our space weather talk, you'll learn more about that. Thank you all. So if you can make it later in the week, we're so excited to have you, and thank you all.